Devo dire che comunque al termine della serie di incontri poi c'è un momento di confronto, quindi eventualmente annotatevi cose importanti di cui volete parlare. Sì, ok. Sì, prepariamo il secondo incontro di questa prima giornata. Sì, con Roland Sottek, benvenuto. Mettiamo in pausa.
Chi c'è adesso?
Sottek.
Sottek.
Meglio lascia stare. Ta. E tra poco partiamo perché siamo molto in ritardo, quindi se c'è qualcuno che deve entrare e sente la mia voce dall'interno, accomodiamoci. Roland, ci sei? Siete pronti, tecnici, amici?
Non si vede al momento là? Ok.
Prima partiamo con lo streaming dove si vede.
Okay.
Benissimo, partiamo. È il secondo incontro di questa prima giornata con Roland Sottek, Head Acoustics in Chalmers. Chalmers. Il modello di percezione Sottek.
Sì.
Prego.
Grazie. Yes, I was asked to talk in English, so if there are some questions in Italian, I will also answer then in Italian if it's possible. So the title I've chosen is Psychoacoustic, the Future is Now. And it's about my hearing model, and especially about psychoacoustic parameters like loudness, tonality, roughness, fluctuation strength, and there will be other parameters in the future. So I don't know who has heard about psychoacoustics. So why do we need psychoacoustics? What do you think about that? Is there someone here who has some knowledge about that? So what is psychoacoustics? Why do we need that? Yeah?
See, one.
But there are not many. Maybe, okay.
I think there are opinions as well, but I think psychoacoustics is just, with a focus on the perception side of the whole auditory system, going away from the bare physics, numbers, and looking into the actual perception, which makes it difficult because a lot of other things come in as well, right?
Yeah, that's right. In technical acoustics, we're looking to levels, spectra, and so on. But we are focusing on the recipient. The focus is on human perception. And my lecture in Sweden is also called, not psychoacoustics, it's called Human Response to Sound and Vibration. So there we have also the interaction between the senses, so vibration and sound, for example. But I'm talking only about sound today. So the question I asked was, why do we need psychoacoustics? And here we see one example. And this is something to convince people that they don't knowing about psychoacoustics. So we have here two files, two sounds. We see on the top pictures the sound signals. So I think here we have the sound signals. And in the lower part, we see so-called third octave spectra, and also the overall level. Sometimes people are looking only for overall level, but other times they are looking also for the distribution of the levels over frequency, and then with a certain resolution, logarithmic resolution, third octave spectra, and we see that for the two sounds here. We see that the amplitudes, the sound pressures are almost the same. Here we have more changes over time maybe, but if you look to the spectra, they're almost the same. And now I will play the two sounds, and we have different sensations, I hope so. So for the first sound on the left side, so that's somehow annoying. I stopped it here because it's a continuous sound. And now I'm playing the second sound. So the first sound was an electrical motor, and the second was a part of a Mozart concert. And here we have a clear difference in our sensation when we are listening to these sounds. And if someone tells me, okay, the overall level, or A-weighted overall level, or even the third octave spectra are the important things, I say, no, that's not. What are the differences here if the third octave spectra are the same and the overall level is the same between the two sounds? Do you have an idea? What could be the difference? Why do we have a different experience here? It's a very simple thing. So what people are looking, if you are calculating the level, is an overall value. But if you look into the spectra, we have an average spectrum. But there's more. We have time structure. So that is that the signal is changing over time. And if you calculate some average values, like average spectra or overall level, we have only a limited view on that what is happening. And with the time structure, the spectrum and the time structure, everything is important. And if you miss one of these, it's like the if you have multiple senses. If you miss something, we miss some. We have not the complete picture of that, what's going on. And on the right side, I have put only the third octave level together, that you can see that we have almost identical levels and third octave spectra, but with different sensations with these sounds. And especially if you are going to sound quality, that means we would like to evaluate the sound. How do we perceive the sound? And this is a very important task in product design, but it's not only important in product design, it's also important in room acoustics, it's important in musical acoustics. So I was invited to give a lecture last week at the University of Detmold in Germany. There are musical acousticians trained, and I showed how to do jury testing and how to evaluate psychoacoustic parameters and to collate that together. And this sound quality evaluation is a very important task, because people don't want to have disturbing sounds, and this is very often a challenge. We have some disturbing sounds, like tonal sounds. I think tonal sounds should be known for everybody what a tonal sound is, but we have also other sound patterns, so spectrotemporal patterns. That means we have changes in frequency and time, so-called modulated signals that cause sensations of roughness and fluctuation. I will play some examples in the next minute. So we may have changes in the amplitude of a sound, but we may have also changes in the frequency of a sound. So the frequency of a sound is going up and down, and this causes these spectrotemporal noise patterns. And this has nothing to do with level, and this will not change that much the spectrum. So the time structure is here also very important. And another aspect that we have to consider is that sound quality can also affect the health and well-being of people. So that's not only related to the overall level. So you may have a sound that has a much lower level than another sound, but it may cause more health issues than the sound with the higher level. And this may cause, for example, sleep disturbance or cardiovascular effects and cognitive impairment. So I developed a model, and that was started around 1990, but it was improved during the last years. And my aim was to explain and describe with one model many psychoacoustic effects and parameters. And recently means during the last 5 to 7 years, these parameters were standardized in ECMA standard. This is an international standard, and the name of the standard is 418-2. And we started there with tonality. Then that was before in another standard, but in 2020 it was coming into the new standard. Then roughness was added and loudness. And recently, that means last month, also fluctuation strength was published in the most recent version of this standard. And these standards can be downloaded for free. In other standards, you have to pay for these standards, but these standards can be downloaded. And there are also now some open source implementations available also for calculating these parameters. So let's come to this, what I promised. What are these modulated sounds? How do they sound? And I have here a very simple example of a 1 kilohertz tone that is modulated with respect to the amplitude. So the amplitude is going up and down over time with a certain rate. And the change is maybe for every second. That means we have a modulation rate of 1 hertz. Then it sounds like this. So we can follow that the level is going up and down. And this causes fluctuation strength. And if we change the speed, how often we have these changes, so the modulation rate, then we have, for example, with 4 hertz, the maximum of the perceived fluctuation strength. And this is very often used for alerting sounds. And if we look to speech signals, so the envelope of speech signals has also these 4 hertz, and this is for our communication very important. And so we are attracted by these sounds, but these are also very annoying. So normally we don't want to have these sounds, only in some cases where it's really necessary. So if we then increase this modulation rate again to 70 hertz, say, then we have another psychoacoustic parameter that's called roughness. So we can't follow any longer this changes in the amplitude that makes a constant sensation. And this is also a very annoying sound. So this is about the time structure and the parameters fluctuation, strength, and roughness. I will not go this morning, due to time reasons, into the details of fluctuation and roughness. I will focus on tonality and on loudness. So when we are performing evaluations, we are not considering only one parameter, for example. So we are looking how rough a sound is, how fluctuating a sound is, how loud it is, and so on. So especially in very complex sound scenarios like soundscape applications, we have many sources and we have to find a way to evaluate this. And very often people are using linear combinations of some of these psychoacoustic parameters like maximum, average, or percentile values. And, individual events may also cause a bad or good perception. Mainly, most of the cases we have a more annoying factor if we have high tonal individual events, for example. And there we have to consider how often they occur, what the magnitude and the frequency, what the magnitude and the duration of these components is. So especially individual tonal events, if they have a certain duration, if they're very short, they're maybe not affecting the perceived quality that much. But if you have sounds that have a duration of a second or so, even if you have a very long observation interval, that means we have a sound that is presented for a minute or so, a tonal event may cause just an effect if it has 1 second. And that has to be considered. And if we look for some statistical values like percentile values, they do not consider that in the right way. So I'm going now to talk about tonality and loudness, and I will have also some application examples at the end with respect to some interesting topics that are high topics. So that's about drone sounds, unmanned aircraft systems, and heat pump systems. Yes?
Does the frequency affect the perception of roughness? Like in the previous
what do you mean with frequency? Do you mean the modulation rate?
No, the
absolute frequency.
The absolute
so
frequency.
You have a tone, or you have a broadband noise or narrow band noise at a certain
Yes.
in a certain frequency range.
Yes, if you play a higher frequency, like the one you showed, was 1,000 hertz. I believe.
1,000 hertz that was in the main cases was studied around 1 kilohertz. But if you go to higher frequencies, so there is not they can't see a huge effect at higher frequencies. There's the effect if you're going to lower frequencies,
Okay.
and there's also an effect at which modulation rate the maximum roughness is perceived. So I've given you here the example because of time reasons for 70 hertz. This is for frequencies for 1 kilohertz and above. You have the most sensation of roughness at a set modulation of 7 hertz. If you go to lower frequencies, there you may have also at 30 hertz, at very low frequencies, the maximum of the perceived roughness.
Okay. Thank you.
You're welcome. So if you talk about tonality, then we have first to understand what is tonality and how is it perceived. So I have here four examples. And I'm asking also my students when I'm doing this in the lectures, which sound is more tonal. So the first example is very simple. So I play the first sound. Can you make it a little bit louder, please? Okay. And the second sound? So here it's very clear. So which is the most tonal sound? The first one. Okay, and here we have the first sound was a sinusoid and the second was a noise sound, and here we have to consider dependency on the signal type. So that's really easy in that case. But now we are mixing sound components. So the next example. Did you change the volume in between? So I play it again. Okay, I play it again. But next it will become very loud then, the next third example. Okay, so here it's also clear what it is. I think it's, we have in the first example not a pure sinusoid, we have a sinusoid plus noise. And in the second example, we have the same sinusoid, but with more background noise. And here we have to consider the signal-to-noise ratio. So the signal-to-noise ratio is influencing, so the tonal component is partially masked by the background noise. So if you talk to the experts, so this is masked, what we call it. And so we have reduced tonal component due to the background noise. The next example, okay, I think this is okay now. So this is the same sound as it was played before. And now, so here we have the same signal-to-noise ratio, but different overall level. And this was studied also for a while, that at the beginning people said only the shape of the spectrum is important for tonality, but now there's a consensus that the overall level also is influencing the overall tonality. So we have here the effect on level, the dependency on level. And the last example I have here is the following. So here we have the same signal-to-noise ratio, the same level, but different frequencies. So we have here to consider that the sounds with different frequencies also cause different loudness. So a tone at lower frequencies is perceived less loud than a tone with a higher frequency or a mid-frequency range, for example. And here we have the dependency on frequency. So these are the main factors that influence the perception of tonality. And tonality has a huge practical relevance in many applications. So in automotive, aircraft, IT, environment acoustics, also music, room acoustics, everywhere. And especially e-mobility in the automotive area increases the importance of this effect, because there we have more tonal sounds due to the electric motor. We have also to deal with higher frequencies because we have higher rotational speed. And we have less masking due to that we have no combustion engine. That causes also mechanical background noise, and it does not mask any longer these tonal components. And what we like to have is an automatic quantification of the different dependencies, signal-to-noise ratio, level, frequency, and so on. So I will give you now a short introduction how my model is dealing with tonality and also with loudness, and without showing you the math. So you can find the math in the literature, or you can find it in the standard. If you would like to implement it, you have to be an expert in signal processing. But for me, it's important that people understand the basic principles of the methods, that you understand what's the benefit of this model and what's maybe also the advantage compared to other models that are existing. And here we start with this, always with the sound pressure. We have a recording, and the recording can also be binaural, and we will hear a little bit more about binaural listening and binaural processing later. But we have two channels that were recorded, like the ones that I've presented before. I did not talk about that. We have left ear, right ear, and we have measured here wind turbine sound, for example. That sounds like this. You clearly detect a low, mid or low frequency tonal component that is almost constant over time. So we have here the time signal. You can see that here. Yeah, the mouse pointer's there also. And then we are going into the frequency domain. So there are different steps in between. So we have to consider the filtering function of the outer ear. So if a sound wave is coming into your ear canal, so we have reflection, diffraction at the head. And this is done by some filtering in the beginning. And then we're coming into the inner ear. And then what we have there for the next main step is the so-called specific loudness. And we see here the frequency axis here. And here we have the time axis. And the level or the value of the specific loudness are coded by colors. So the white and yellow colors are meaning these values are very high. And if you look here around 700 hertz, this is the influence of this tonal component that we have heard before. So we have also here more signal components. We have here also a structure where we can see we have here higher specific loudness, here lower, here higher. So we have also some fluctuation there. There are many other effects in this sound, but the tonal component is one very dominant component here. And if you would have a pure tone, a sinusoid that is constant over time, then we would see here only a constant value over time. There would be no changes, but we have still a distribution over the frequency. And here at this frequency axis, I could also put the numbers of the critical bands. So the incoming signal is filtered by bandpass filters. And then we have the representation of the critical bands with some overlapping therein. But we have always, even for a pure tone that would be represented in the physical, as a physical spectrum with a pure line or so, we will have a distribution here over the specific loudness. The sum of the specific loudness would lead to the overall loudness for a certain time instance. And if we have a constant signal here, we would see the constant loudness over time. So this is the basic principle how we can deal with such a picture. Here is the most information. We could reduce this information summing over the critical bands. Then we would have an overall loudness over time, and from that we can get a single value, a number that people normally would like to have at the end to evaluate the sound with respect to loudness. If we do that for frequencies, for different frequencies here, we have here a frequency axis from 100 Hz to 10 kHz. We can then calculate the loudness for different tonal components, pure tones, at different levels. And what I've shown here on the right side is only one result of the algorithm that's related to the so-called equal loudness level contours. And these equal loudness level contours show us what is the level needed to generate sound with a certain overall loudness. If we have 1 kilohertz, 20 dB, then we have here a certain loudness. And if we would compare this to a tone with another frequency, here at 100 Hertz, for example, we need much more level in order to generate the same sensation of loudness. We need there more than 40 dB for 20 dB at 1 kilohertz, and so on. So, and one benefit of my model is that I can simulate this so-called equal loudness level contours much better than the other standardized loudness models. So the next step is, and this is due to better nonlinearity in my model. I have not the time to explain that in detail, but there's another effect that I would like to show you now. That is, with my model, you can separate the tonal component and the background noise. So this is a very important step. There's a question?
Yes, only the question about the model and the graph to the right. Is it based only on pure tone or yes?
This here, we have here we have here. I don't know. I think you can see that there is a dashed line here, a black line. This is the ISO 226 220 from 2023, where I was the project leader, where it's described how should the equal loudness level contours look like. And the blue curve is the calculated result using my hearing model, and this is almost on top of this curve. There's only a very small difference, 1.5 dB in average for all the data that is presented here. But this is for pure tones. So in the standard, these only pure tones are covered, and so there is no other standard that is related to narrowband noises or so. But this is also a special case. Normally you don't need, I would say, this standard, but people would like to have such thing for pure tones. If you would like to know what the loudness of any sound is, you should use a good loudness model, and then you can predict the loudness with the loudness model. So the equal loudness level contours is only one application example of a loudness model.
Another question is, how are these curves parallel? Why, sorry?
They
Why?
are not parallel. They are not parallel.
Yeah.
There are differences here. They are not parallel, so even at very low frequencies and at higher levels, they are coming okay. More together. They are not parallel. Here, for example, at 100 Hertz, we have between 20 phone and 40 phone, maybe it's 20 dB, and here it's about only 15 dB or something. So they're coming narrow. So because of the presentation size here, it's very hard to see, but there is a difference. They are not parallel. And therefore, it's also not good only to use A weighting. So the A weighting is related to the 40-phone curve. And this is only one shape that you are using there. And this is also very smooth, the A weighting. So even for that case, A weighting is not enough. So let's go to the next step. So that is what I said. One important step in the model, and this is cannot be found in the other models, is that I can separate the tonal content from the noise content. And you see the result here, and this is the tonal loudness, that is the loudness, what we see here, that is related to the tonal component only. So if you look here, you have an idea that this part is related to a tonal component. There's a strong band that is here with a high value of specific loudness. And the algorithm provides us now this result, and this is related to the loudness only of the tonal component. And this is not the end of the algorithm. There's also, at the end, a consideration of the signal-to-noise ratio, and this means here, in that case, the ratio of the loudness of the background noise and of the tonal loudness and of the loudness of the background sound. And this changes here, in that case, only a little bit. You see here, if I'm considering this here, you see a small effect, but not that much. But if the background noise has a higher value, you would see a stronger effect here. So it's considered, but for this case, this effect is not that important. And I would like now to go to the next, if there are no questions about that, and at the end, we get the tonality here, taking the maximum of the specific tonality as a function of time. There's no summing at the moment for this tonality algorithm. If you have multiple tonal components, then I use, at the moment, the tonal loudness only for the multiple tonal components. There's another question. Can you give him the microphone, please?
Yeah, I was wondering if like the examples you showed were about sinusoidal tones, right? Like 1 kHz.
One moment. The equal loudness level controls.
The next one?
This one. Yeah.
So I was wondering, what if you use the different fundamental frequencies which have a lot more harmonics or less harmonics? Like, what if you compare, I don't know, a trombone to a string instrument which have a really different spectral disposition of harmonics?
No, here for this standard, ISO 226,
okay.
Only pure tones are considered. Pure tones are considered with different levels and with different frequencies.
Okay.
And you compare always to 1 kilohertz.
Okay.
And the procedure is you calculate for 1 kilohertz the loudness, and then you adjust the level of the other sounds that the algorithm shows at the end the same value as it has shown for the 1 kilohertz. And the value of the loudness is not important here in that case. You can use this for any model, even if the models are showing different results. So my model, by the way, is using the data in the literature much more in detail without oversimplifying something. So my model provides lower values of the loudness compared to the other ISO models. But using my model for different applications, you can see that it matches very well with the results. But if people say it in the past, there's this rule of thumb. 10 dB change in the level will lead to double loudness or half loudness in which direction you're looking for, and this is not correct. So it's depending on the level, the overall level, and if you look for the, for me, most interesting level range from 40 to 80 dB, you have as median values maybe 13 dB that is needed and not 10 dB, and this makes a huge difference. So that leads to difference of a factor of 2 or 3 if you are going to very high levels. So if you're applying the other models for environmental sounds, you get maybe 50 sounds, and if you're comparing that to the loudness of a 1 kilohertz tone with 40 dB, you have difficulty to say that's 40 times as loud as that it is. So you have to do your own experiment. I did this, and with my model there the factor is 2 times lower or 3 times lower, depending on the level range that is considered. But this is matching better the results of the jury test results. Other question? Okay.
Yes, very interesting. So it's very clear it's dealing with tones, pure tones, at different frequencies, and stationary, right? Stationary signals. How about the masking signal? Is that dealing with broadband noise only, or narrowband, different maskers at different frequencies? Does it incorporate...
For this example?
Yes,
there
in
is
general
no
about the
background
model.
noise.
Yeah, I mean the... okay, that's clear.
So for the ISO algorithm, you are using really pure tones. And for that case, there is also no need for separate tonal sounds and background noise. Then the overall loudness is the same as the tonal loudness. So that's very easy to compare. So, and the other algorithms don't have the disadvantage that they don't have the separation algorithm. But I will show you another example where this separation of tonal and background noise and a new combination of these tonal and background noise loudness lead to much better results compared to the other algorithms. I will show that later.
Okay, thank you.
Okay, but this is very interesting. And what about this increase in the model across between 1 kilohertz and 2 kilohertz?
Increase? What do you mean here? I don't know.
It is not linear, but it is okay.
Here, this,
yeah.
and this.
Yes.
So here's 1 kilohertz and here's 2 kilohertz, and this shape also what it is. So this is the shape that you get also from measurements. So, but you are thinking, what is the effect in the ear where it's coming from? So of course you have some principles there. You have the resonance in the ear that is changing also there something. So you know that you have a lambda a quarter resonance there, and then you get much more level. And so you need here less level if you are going to higher frequencies in order to have the same perceived loudness.
I would have expected this at in between 2 and 3.
Here, yeah.
A little bit.
When here the curve is going down, that means that the signal is higher due to the amplification of the resonances in the ear. So this range here around, this is a broader range. If you are talking about this detail here, then this is due to the amplification of our ear canal, and so this is the reason why we don't need that much level in order to perceive the same loudness. Okay, so I see I have to shorten my presentation, so there are so many questions. But it's very interesting. Don't hesitate to ask me. So I like this interactivity, and I like this kind of
yes, it is expected that the questions are useful to understand more of what he says, but it is not a problem for you if you have to shorten your presentation, because otherwise people do not understand, and it is...
Yeah, thank you very much for that. So, I'm happy for that. So I would like now to show another algorithm that is called prominence ratio or specific prominence ratio, that is very often used in industry and is also standardized. And this looks for the third octave spectra, or here in that case even for the critical band resolution, and looks where do I have a spectral component that is dominant. So you see here in the frequency range around 700 hertz, there is a peak, and around this frequency the critical band level is calculated, and compared to the critical band level to the left and the right, the average of those, in order to see, is there a spectral peak? So, and the only thing that is considered is the level difference in this critical band compared to the average of the left and the right band. So, if we are looking only into differences, this will mean that if we change the overall level, the difference will remain the same. So, we have one component, we have some noise to the left and the right, and we are calculating the levels, and if we look for the level difference with this procedure and we change the overall level, the difference will remain the same. Only that the values are higher or lower, but the difference will be the same. And this difference is then used normally to describe tonality. And this has a drawback. This is a drawback here for this algorithm. So I will play first the original wind turbine sound. So, and I'll explain what's showing the second picture that looks the same. I reduced the level by 20 dB. So it's not a fault here that it shows the same. So it's the principle of the algorithm that does not cover the overall level, or to use the overall level, only the difference in the neighboring bands. So you can hear the sound. There's a small amount of tonality, but it's much softer with respect to the tonal loudness or the tonality. And if I play it now with plus 20 dB, okay, it's too loud here. So, but the effect is clear. The tonality is changed by the overall level, and this is not considered by the specific prominence ratio. And if we use the hero model tonality, we see this difference. So we have the original sound with this tonality here. This is with the lower level, and this is with the higher level. So we have a correlation that corresponds to our perception. Okay, now I will summarize this. We have tonal sounds that are perceived very prominently and can lead to high annoyance. And if we compare different methods that are standardized, we have different results. All the methods consider the signal-to-noise ratio. Like the prominence ratio, we have there, if we change the background noise, it will also has an effect on that. But there are this prominence ratio, there are other algorithms, I did not mention that up to now, tone-to-noise ratio, or there's a DIN algorithm also, and my hearing model tonality. And if you go to the other dependencies on level, there's only my model that is using this information. And the dependency on frequency is partly also covered by the other algorithms. But if you look into the standards, the other algorithms are not applicable to non-stationary sounds, even if we use that. So we are using it, we segment the signal into blocks, we analyze the prominence ratio, and we go to the next block. We can do that, but the algorithms in the standard are described in the way that are not usable for non-stationary sounds. And so the previous tonality standards lead to unsatisfactory results because psychoacoustics is not taken at least fully into account, and they are not applicable to non-stationary sounds.
How can you be sure of that? So have you investigated with questionnaires or apart from the algorithm, have you investigated this with perceptive tests? That is, so people.
So this, for example, the dependency on level, you don't find a part in the algorithm that is considering that it's not there in the algorithm. So I could do there are so many tests that I would like to do. So this test doesn't make sense because there's no part in the algorithm, the signal processing that is taking that into account, for example. And this, as I mentioned, we are doing this also. If you trust in the prominence ratio, for example, you can try to apply it, but in the algorithm, in the standards, there is given, you should not, it's not written, you should not use, but it's only intended to be used for stationary sounds. And stationary sounds, according to my opinion, are not existing in real life. So we have always, these are only synthetic sounds that we could generate, but if we are doing, if we record sounds, we have always in stationary, time-varying sounds. Yeah. And there's another parameter, so there's tonal annoyance, that is different from tonality. If we look for tonality, it's strongly related or correlated to the tonal loudness, or the loudness of the tonal components. But loudness is not the same as annoyance. So if we go to higher frequencies, so for example, 2 kilohertz, 4 kilohertz, 10 kilohertz, so if we have the same loudness at that point for tonal sound, people are more annoyed by that. So I did also, I would like to answer a question. Now, there I did experiments, so where we asked people to adjust the sound that is equally loud. Okay, we find then the equal loudness level contours. And I asked people also to adjust a sound referred to reference sound that they perceive the same annoyance. And then you have a much higher reduction at higher frequencies. So you can find that the higher frequency tonal components are more annoying, and you can then use this, and I did this also with different levels of the sound, and it had the same effect there. So you can weight the tonality in the way that the higher frequencies cause higher annoyance, so with a weighting function. So that is really easy done, and so it's not at the moment in the standard, but it's published, and it will be maybe, if I have time to put it in the next standard, I will do that then. And I have another option here that is not mentioned in the standard, but is using the data that is in the standard. So we have here on the right side the specific tonality for all-wheel drive electric SUV. And here's a special representation. It's not frequency that is used here. So it's a rotational device. I don't know if you're familiar with that. Mechanical engineering should know that. These are orders orders. We have here pretty high orders. So we have a rotational speed, and if the rotational speed is changing, also the frequency components are changing, and the order analysis makes that as a flat function. So in order to better understand where this phenomena is coming from. But the frequency resolution in the hearing model is normally based on the critical bandwidth. So you know you have a tonality in a critical band, and you know the value, and you're fine with that if you're interested in the tonality itself. If you're not interested in the frequency of this tonal component. But if you would like to change your product, you are interested, but it's the frequency. So the frequency is available in the algorithm. So it's also described in the standard, and I can use this information in an additional plot. So here I'm using only the resolution of the critical band. So at low frequencies, the critical bands have a bandwidth of 100 Hertz, and you don't see, is it the frequency, is it 90, is it 70 or whatever, you don't see that there. You see only that there's a tonality. But I can use this information and put this in another plot, and then you see on the left side, with another axis, this based on the frequency itself that is available. I can plot then here also the same tonality values that you see here, but you know now where the frequency is, and this gives you the opportunity to say, okay, this tonality is due to the 94th order, and this here is due to the 187th order. So this gives more insight into the physics, into the causes, which part of the product is generating these tonal components. So, what's another question? Okay.
The question, sorry. But if I understood well, your model of tonality does not take into account the annoyance due to high frequency tonality. Is it correct? So
no,
only detects tonality.
So the model calculates the tonality. And the tonality is defined as the tonal loudness,
presence,
considering also the background noise. So that's the tonality. And if I would like to calculate the tonal annoyance with my model, it's available, but it's not in the standard at the moment. I have a weighting function that is known. I published it at Internoise 2019 in Madrid. And you can apply this, and you get also the annoyance of the tonal component.
This is very important, in my opinion, for I don't know, the experiments.
Annoyance. I can talk about annoyance. Annoyance is not a psychoacoustic parameter. It depends on so many things. So if you would like to evaluate annoyance, you have to look for maybe also for fluctuation strength, for roughness. You have to look for also for loudness itself. So there are so many, and you have also to consider the context. So where are you listening to the sound? What is the environment where you are? And this may affect, of course, the annoyance. But we can also, I did not talk about sharpness, so this is the next step. There is no good sharpness model at the moment. And I have an improved model, but I'm still working with a PhD at the University of Salford in order to improve this model. But this will need a while in order to come to a validated model that can also then be standardized. But sharpness of tonal components is also affected by the frequency of the tonal component. So if you would like to develop a new metric of annoyance of pure tones, one could also think about combining the sharpness and the tonality in a metric in order to get the annoyance. But with this weighting function, I found a way that is easier to apply without considering another psychoacoustic parameter. So, but tonal annoyance, tonal loudness are different things. Tonal loudness is the basis, is also the basis for the overloudness. I will show you in the next step. And annoyance is easily done by weighting the tonal loudness at the end. Parameters for annoyance, for general annoyance, for general annoyance. But if you are talking about annoyance of tonal sounds, there is no other parameter that you could think about that is known at the moment that would cover the higher annoyance of higher tone components except sharpness. So there is no roughness, there is no fluctuation strength for a pure tone. So I don't see another parameter that can be. Tonality and sharpness, yeah. I would say yes. If you are talking about pure tones, if we are talking about multiple tonal components, then we have to consider dissonance, other things. Then also roughness is coming into the game, and also maybe if their tonal components are very close to each other, we have fluctuation. I have some examples later. So for pure tones only, we have these two parameters. Yes.
Sorry. May I just come back a little bit to the model, just to have a clearer picture? So, okay, the tone is a tone, and we can see that the tonality depends on level, signal-to-noise ratio, and other aspects. When, okay, the level can be the level of the tone, of course, the target tone. For the signal-to-noise ratio, the examples were related to broadband, maskers. So I was wondering, does your model incorporate different maskers, different competing sounds, such as narrowband noises or other tones, if you think it makes sense? Yeah. And the second aspect is related to the, let's say, modeled individual, which is behind average individual, let's say, listener, which is behind the model. So the duration of the stimuli are there in the order of seconds or minutes. So is some sort of adaptation or fatigue incorporated into that? Do you think it would make sense? And also the, let's say, individual abilities, how possible changes into individual auditory abilities, for example, dynamic range, loudness, perception, may affect that. And again, if you think it makes sense to have those kind of more, let's say, individualized models. Thank you.
Many questions. So I will try to answer them one by first the first question. So you talked about the shape of the background noise. So broadband or narrowband. So and the duration. So these two topics. So I did experiments, and I used also experiments from the literature. They were using very short signals, like 2 seconds to 5 seconds. And so if you have constant sounds, you don't need that long. The fatigue in listening tests should not be lasting more than maybe 15, 20 minutes, maximum 30 minutes. So people are going to be tired after a short while. And I'm also using techniques in order to test this. What is the best way to do such listening tests? But this is beyond this topic. We have another day, other days in order to discuss this. The effect in the model, if you have a broadband model noise, then that would not affect the tonal sounds completely. It's only a part of the background noise that's affecting. So if you have very narrow band sound components, this will be covered. But for the broadband noise, there will be a limit, maybe covering 2 or 3 critical bandwidths in order that will have an effect on the masking of these tonal components. So I could talk more about that, but the other point was sometimes I'm using longer durations when I'm looking for the effect of single events. And there was a paper published in Japan, in Chiba, at Internoise 2023, where I used masking background noise, 40 seconds from soundscape recordings, and I inserted several single events in order to evaluate the effect of the events. And there was a clear effect on single events with a certain short duration, even if this is not covered by the so-called percentile value, how often a value is exceeded in a certain amount of time of the complete duration of the signal. So, but in order to answer the full set of questions we have to discuss this more in detail later. So I hope I could answer at least some of your questions now. Are there other questions? Okay, so I have 50 minutes. We started later, but maybe I cannot show the nice examples at the end. If you would like to see them, we can make it in the break or so later, but I don't want to extend the day too much. Okay, so we will see. So now we're coming to the hearing model loudness, and here's also the question, why do we need just another loudness model? Of course, I could say, okay, I have a model, I can calculate with this model all the psychoacoustic parameters, okay, I'm calculating also a new loudness model, but why do we need a new standard and so on? So I have just shown you one example, why it's really interesting to have this, in order to use the most information that is available in order to have a model that uses all the information that is provided in the literature, or almost, at least that I know. I could better match the most recent equal loudness level contours. That's a huge benefit, I think, even if it is a special case only related to pure tones. And the much better point, for my opinion, is that it considers better the tonal sounds. And I will explain this in a historical review here. So, because the assumptions from the beginning of the loudness studies in the last century, they were oversimplified. And you may know that the critical bands are bandpass filters or bandpass signals or related to bandpass signals where the intensity is calculated in each of these critical bands. So this was used by Stevenson, this was also used by Zwicker, and they said what is important is the intensity, the level within one of these critical bands. It doesn't matter how the shape within the critical band is. If you have a narrow band noise, you have a certain level, and or if you tone, doesn't matter. But this was oversimplified. But this was used then also in the ISO, Zwicker, and Moore, Glasberg, Schrittlacher loudness models. And there were just, I think in the 70s, more than 50 years ago, Zwicker showed also that it has an influence, that the tone is perceived much louder than a narrow band noise and so on. But it was not used to correct the standards. It was not used there. But this was also only a result. So, and I did also some experiments in 2010, and other people used tests also that show that a critical band with noise and an equally loud tone, that means the narrow band sound, the bandwidth is one critical band and a tone, and they are perceived at the same loudness, they do not have the same sound pressure level. And the equally loud tone may have a sound pressure level that is around 7 dB lower. And 7 dB is a lot. If people are looking for enhancements to reduce the dB there and the dB there, so 7 dB is a lot. And that means also at the same SPL, the tone is perceived significantly louder than the critical band with noise. So I think this is some important information you should understand. If you have questions, please ask me now. I can repeat it with other words, or maybe Ariana can explain it with her words. That's clear. Yeah. So ISO 532, maybe Zwicker, Moore, Glasberg, Schlittlacher, underestimates the loudness of pure tones compared to noise.
Only the question is, Roland, but the noise, the critical bandwidth noise, okay, what kind of noise exactly?
I will explain it now, coming now to one of these experiments. So there are different publications that I made where I compared all the experiments of other people, but I have one example, but it shows the same tendency as the other experiments. I will show that. So, and with my model, you can get a higher accuracy of overall loudness. So, and here we have the experiment of Horst Rennis Verhey. Maybe some of you know Professor Verhey. He does a lot of nice papers in JASA and is also editor there. So what we are comparing is a tone with a frequency of 1.5 kilohertz. That was done mainly by Horst here, but with a level of 50 dB. So one frequency, one level. And the noise signal is Gaussian noise centered around this same frequency, so in the same frequency range, with varying bandwidth filtered, but with very steep slopes. So that's the only. So one could do also one could also use lower slopes there. That will also change then the results. But this is what they used. But what Zwicker did was not this kind of noise. But here this is one of the experiments. So. Then they determined the point of subjective equality with an iterative 2AFC procedure with 10 subjects. And what we see here is the mean value in the center here, the symbol, and they have the standard deviations. So they adjust the two signals, and at the end, in an iterative procedure, when the reference signal was fixed and the one signal was changed, and at the end they get then at the same loudness, we get level differences. So what is shown here is the level of noise minus the level of tone. So that means if you have a very small bandwidth, the mean value is the same, so we have no change. So that means that a very narrow band signal is considered to be a sinusoid or something like that. But if you go now to here in that range, we have the critical bandwidth at 1.5 kilohertz. It's here in this range. We have here 6 dB, but it goes up maybe up in the standard deviation if you consider that to 7 dB and here, maybe a little bit lower. But there's a strong effect and significant effect that this is perceived only at the same loudness if you increase the level of the narrowband noise. And now I have plotted the results of the algorithms, and I was using the algorithms. Huh? I have used here the ISO 532 with different single values. So at the end, one can discuss what is the right single value. So the value that is exceeded in 5% of the time, or an energy equivalent level. So at the moment, we don't consider these values. They're also very small here to read. For me, it's really difficult to read, but we have here also the ISO 5323. This is from Moore, Glasberg, Schlittenlacher. What we can see here is that all the symbols are lying here in the range almost below 0 dB. That means an opposite effect. That means we have to change. We have to reduce the level of the narrowband noise in order to go to come to the same perceived loudness. So this is not that what I would like to see, but it's going always in the wrong direction. Maybe there's some small here in that case, maybe it's close to 0, but in average it's maybe at -2 or something like that. So, and if you apply my model, then you get the green symbols here. So they are almost lying very close to the mean value, but they're also within the standard deviation. And you can do that with many other tests that I've found. And I did this also in the Dager paper in English. You can also read that. So you will find that is a huge benefit of that. So to conclude this, several previously published experimental studies shows positive level difference between a subcritical bandwidth noise and equally loud tone. That means we have plus 7 dB or so, 5 dB plus for the critical bandwidth noise compared to equally loud tone. And this is not shown by the ISO standards. They are underestimating the loudness of pure tones. And I did not show the formula here. So I'm using a nonlinear combination of the tonal loudness and the loudness of the background noise. And the background noise is weighted with a factor less than 1, so that it's reduced. And so that the tonal loudness is more important with respect to the background noise, but it's not a linear combination, it's a nonlinear combination. So I don't want to bother you with this formula here, but the idea should be clear that I have a combination of these two components of the loudness. And I would like to conclude also with my vision that I have with respect to psychoacoustics, to make psychoacoustics better understandable, not with very complex algorithms. So there we have to have experts in signal processing to understand and implement them. But I would like to have an understanding that if you have a parameter, with the value of the parameter, you know exactly, is it important for me or isn't it important for me? And if you look for the tonality, we have here small values, 0.1, that's barely perceptible, 0.3, easily perceptible, and 1 tonality units, HMS is here in model of Sottek, strongly perceptible. Everything that's above is not something you would like to have. Even 1 is a high value that you normally don't want to have, except when you're looking for musical sounds. So they have tonal sounds, they have melodies, that's another topic. The magnitude of perception should be also the same for the other parameters, but to give you an idea what 1 tonality unit means, this corresponds to a tonal loudness of 1 sound. That means as like an 1 kilohertz tone or 40 dB. And if you go to roughness, we have another unit, but here the scaling of the psychoacoustic parameter is the same, that you also know if you have a roughness of 0.5, it's something significant. And if it is 0.1, you don't have to consider this. And I have reviewed many papers and research projects where people were looking for correlation with respect to roughness, and they had values of 0.2, 0.4, 0.02, 0.04, and 0.08, small values. There was no roughness, but they didn't listen to the sound. So I encourage you, listen to your sounds and understand what parameter is there. So we have to be trained in order to understand what is going on there in the sound. And if you apply if you're applying a sound without thinking about to use it, then you can come to good correlations, but the correlations are not because there is an important impact of this factor. It's more that there may be a loudness-depending factor that shows this high correlation therein. And for fluctuation strengths, we have also the same, and same value means same magnitude of perception. What I would like to improve in the future is to use new experiments for determining JNDs of psychoacoustic parameters. And this is ongoing just at some universities, and I would like to encourage other universities to collaborate. And this is something I'm really interested in. We learn a lot, and we have a lot of advantages. So we make papers together, international papers. We present that at international congresses and conferences and so on. And I have contact with Giovanni Brambilla. We had on Tuesday? No, it was the day before I was here arriving, so it was on Thursday. So I'm traveling around the world. I don't know which day it is. So, but this we discussed this that to have also in Italy maybe a kind of national project. But I'm doing it for fun. And I can also provide some lectures. We can go more into detail also in psychoacoustics, also in jury testing, if you like. And then we will do tests. And really you learn by be trained and learning also this on the way. So my time is over, but yes. I didn't have presented examples. So, but maybe another time then here. So.
Thank you. Other questions, if you have one question, otherwise later, okay?
I wanted to, well, thank you for your presentation. I wanted to ask about the psychoacoustic reason for this level difference between the noise and the pure tone, where the noise was following the equal.
I don't know the reason why we are expecting or why we are evaluating tones in a different way than the background noise. So I have a model, but I can't prove that we have something similar in our brain that's going on there. So I have no capabilities to look there in, and I don't have technologies in order to test this. So what I can do is I can look for experimental results and see how we can describe this in a better way. And I have an algorithm that separates the tonal component and the background noise by applying an autocorrelation analysis. And this is something that is also mentioned sometimes in the literature, that people think it could go on in the brain, that we have something like that. So this was my motivation. And my motivation at the moment is to describe the parameters or describe the effects in the best way I can do with signal processing. But I cannot prove that this is really the same algorithm that is going on in our brain. So that's I can explain you why some results are showing this way and so on, because I know the algorithms, but I can't tell you where you can find this processing step in our brain. So, for example, I'm sorry about that.
Thank you.
However, this is a very good question.
Yeah, it's a very good question. Yeah. So I was not.
You need a neurologist. I don't know. You need a neuroscientist.
Yes.
I don't know. Audiologist.
Yes.
Just about a very, very, very simple way that can be, let's say, simplified, because you will have a cochlear processes. So you will have stimuli reaching the basilar membrane and the cochlea vibrating, and neural fibers reacting to the vibrations of the cochlea. So you will have also some mechanical aspects at the level of the basilar membrane fluctuating, different sensors activating on the transducers which are in the cochlea, and a different number of nerve fibers responding to that, and different frequencies of the spiking nerves that bring the stimuli to the brain. So a very complex pathway that will lead to a higher loudness, which is maybe also related to the higher recruitment of neural fibers, bringing the, let's say, the electric impulses to the brain. So very complex phenomena which are behind it.
I can add something also related to that. I know how the processing is working, but I can't prove that this kind of algorithm is there. So, for example, I've developed also an algorithm that is providing a high resolution spectrum, and this is based on the excitation pattern on the basilar membrane. So all the different parts of the basilar membrane with all the fibers are excited, but you have always a spread of the information. You don't have something like an FFT analysis where you see a peak at one location, but you have a certain shape of the auditory function. And in my PhD, I've described that this shape of the excitation pattern for sinusoid can be expressed almost in the same way. There's some variations maybe over the frequencies, but you have a certain